Welcome to Fractopia, a podcast exploring the fascinating world of fractals. Fractals are geometric shapes that exhibit self-similarity and infinite complexity. They have fractional dimensions that capture how much space they take up in between whole number dimensions. Fractals are found extensively in nature, mathematics, technology, and art. In this first episode, we'll provide an introduction to the basics of fractal geometry. We'll go over a brief history of how fractals were discovered, talk about their key properties like scale invariance and fractional dimensions, go over some real-world examples, and discuss the types of fields where fractals are now being applied. Fractals are deeply connected to patterns in nature, financial markets, artistic beauty, and even the very fabric of space and time. By journeying into the endlessly intricate world of fractals, we can gain insight into complexity, self-organization, and the fundamental behavior of systems beyond our everyday experience. This podcast will be our guide down the infinitely twisting paths and recursive patterns of the fractal realm. So get ready to think outside the whole numbers. Look beyond the squares and spheres of Euclidean geometry and embark on an expedition through the most complex yet beautiful structures in the universe. Let's fractal. The story of fractals begins in the late 1800s with a mathematician named George Cantor. He was studying mathematical sets and realized that some sets can have non-integer dimensions. For example, a line is one-dimensional, but a zigzagging line that goes back and forth infinitely could have a dimension between 1 and 2. This was a radical idea at the time. In 1904, Helge von Koch took this further by inventing the Koch snowflake. This starts with an equilateral triangle. Then you divide each line segment into thirds and replace the middle third with two new segments to make a star shape. When you repeat this process infinitely, the Koch snowflake emerges with an infinite perimeter enclosing a finite area. Gaston Julie extended the idea of non-integer dimensions to iterative functions in the early 1900s. By recursively applying functions, he generated intriguing fractal patterns like the Julia set. This laid the groundwork for fractal geometry. But it wasn't until the 1970s that the field really took off, thanks to a mathematician named Benoit Mandelbrot. He coined the term fractal, studied fractal shapes in nature, and created the famous Mandelbrot set. Mandelbrot brought fractals into the mainstream of mathematics and science. These pioneering thinkers showed that fractional dimensions and recursive self-similarity were not just mathematical oddities, but intrinsic to the geometry of nature. Their work created the foundations for the field of fractal geometry that we'll be exploring in this podcast. One of the hallmark features of fractals is self-similarity. This means the shape contains smaller copies of itself embedded recursively within. In mathematical fractals like the Sierpinski triangle, the self-similarity is exact. Magnify any small region, and it looks identical to the whole shape. These perfect fractals reveal the recurrence and infinity underlying geometric forms. In natural fractals, the self-similarity is statistical. For example, segments of a rocky coastline resemble the overall pattern. The replication is approximate rather than exact. But across scales, the essential structure remains. This self-referencing recursiveness is why fractals can pack infinite complexity into finite spaces. The complexity cascades through increasing orders of magnitude via the repetition. Artists leverage this cascading self-similarity to create dazzling fractal designs. Substructures like the Mandelbrot set can be drawn at any magnification, revealing more intricate worlds within worlds. So whether in nature, math, or art, self-similarity generates the infinite depth associated with fractals by repeating patterns across scales. It captures the recurrence of form that generates endless complexity. Fractals obtain their name from their fractional dimensions, values that fall between the familiar integers of Euclidean geometry. Think 1.5 dimensions instead of 1 or 2. These non-whole number dimensions arise from the fractals' infinite self-similarity. For a rough line, that zigzags. Its topology is one like a regular line, but it fills more space than a straight line. Its fractal dimension of, say, 1.7 captures its complexity between a 1 and 2D shape. We can calculate fractal dimensions using techniques like box counting. This tiles the shape with boxes of decreasing size and analyzes how the number of boxes required changes by scale. The power law relationship exposes the fractional dimension. So if we tried boxing the coach snowflake, we'd see it takes many more boxes than a straight one-line segment, but fewer than a 2D triangle. Fractal dimensions quantify this in-between complexity. In nature, fractional dimensions describe the mixed smoothness and raggedness of coastlines, organic shapes, and other fractal patterns. The non-integer values reflect the fractionally structured complexity. Fractal dimensions characterize the infinity between finite dimensions. They mathematically capture the endlessly recursive nature of fractal geometry. A key property of fractals is that they exhibit similar structure at all scales of magnification, giving them scale invariance. Zoom in on the Mandelbrot set, and you'll see the same swirl of boundaries and buds repeating. There is no characteristic scale at which the pattern changes. It retains its fractal essence infinitely. This scale-free self-similarity results from the recursion generating fractals iteratively through feedback. Tiny and large features get woven together into an inseparable web. In contrast, ordinary geometric shapes like squares only look similar within a certain scale range before the straight sides start to curve. Fractals never smooth out. Nature leverages scale invariance for structural strength, like in branching rivers and trees, distributing weight across scales. Networks exhibit scale-free structure for resilience and efficient flows. Scale invariance signals deep connections between microscopic and macroscopic levels in physics, biology, and ecology. What starts small propagates through the system. Fractals teach us that the large comes from the small in an endless feedback of form. The pioneering work on fractal geometry opened up a whole new world of applications in diverse fields. In art, fractals enabled creating intricate recursive designs using simple computing power. Fractal-based environments and organic shapes changed computer graphics. In finance, analysts found markets exhibit fractal statistics, indicating self-similarity across timescales. This led to new models of volatility using fractal dimension. In technology, fractal networks balance connectivity with resilience. Fractal antennas improved efficiency by increasing surface area. In physics, fractals appeared in quantum systems, statistical mechanics, and theories of quantum gravity potentially linking space and time. In biology, researchers modeled organisms using fractal growth rules and found self-similar structures in bodies. Fractal geometry described complexity. Across domains, fractals provided a new mathematical lens for understanding complexity, self-organization, and scale invariance in systems. The seeds planted by early pioneers blossomed into a rich field, touching every corner of science, nature, and art. This concludes our first episode introducing the wondrous world of fractal geometry. We covered the history of pioneers like Cantor, Koch, Julia, and Mandelbrot, who developed the foundations of fractals. We explored the key properties like self-similarity, fractional dimensions, and scale invariance that create fractals as endless complexity. We discussed how fractals are found extensively in the natural world, mathematical constructions, art and computer graphics, and technologies ranging from networks to antennas. Fractals provide a lens for analyzing and generating complexity. In the next episode, we'll dive deeper into fractal patterns found in nature across scales, from coastlines to plants to the human body. We'll see how fractals capture fundamental recurrence and connectivity in living systems. For now, ponder infinity by gazing at a fractal zoom video, marvel at self-similarity in a head of Romanesco broccoli, and reflect on how simple rules propagate to create immense beauty and complexity. The recursive journey has just begun.